In this video, we will discuss the solution to problem D, the Omnipotent Monster Killer, from Codeforces round 958, which was the Div 2 round. If you are a beginner to DP on trees, then this is an excellent problem for you to get started, as it covers a lot of interesting concepts from various skill levels. To solve this problem, first we will come up with a simple O of n cube dp approach and then incrementally apply 4 different optimizations to improve the time complexity to O of n square, then to O of n log n square, then to O of n log n, and finally we will achieve a linear time complexity. During this process, we will also see how to analyze the time complexity of some non-trivial DP formulation. And to achieve these optimizations, we will take motivation from the problem of counting the distinct frequencies of elements that can exist in an array. If you want to be successful in competitive programming, you need to focus not just on your skills but also on your mindset during the contest. If you are watching this video, you probably were not able to solve this problem in the contest. And even if you have read the editorial, you might think that the ideas presented in the editorial are so far-fetched that you could have never arrived at that conclusion during the contest. But if you look at the rank list, there are hundreds of people who have still solved the problem. So what is it that enabled them to arrive at the solution? So the focus of this video would also be on the intuition of how to arrive at this solution naturally during the contest by using your previous experience. Because if you are not able to solve this problem immediately, but once you gain some more experience by solving a bunch of new problems on this topic, the next time you see it in the contest, you would be able to apply the learnings from different problems in this particular problem that you see. So our goal is to focus on the intuition part and not just on the ideas part, because my approach does not diverge from the official editorial. But what I want to talk about is how to arrive at that idea, not the proof of correctness of that idea. And since we have 5 different variations that we will cover, I have created a contest on Codeforces, and I have added easy version of these problems so that you can submit your slower solutions and verify that it was correct, even though it was not the fastest solution. You are given a tree where each node contains a monster. In each round, all the alive monsters would attack you with their attack points that they have. But after the attack, you can kill a number of monsters provided that you do not kill 2 monsters who are neighbors in the same round. Your goal is to kill all the monsters as soon as possible while not violating these constraints, and also making sure that the total damage inflicted upon you is as small as possible. Let us start with an easy observation. How long will the game continue for? Even though the problem mentions that the game could practically go on for infinite rounds, but in an optimal scenarios, you will kill at least 1 monster in each round. And since there are n nodes in the tree, the maximum number of rounds that the game will continue for is at most n. So now that our problem has been reduced from infinite rounds to n different rounds, let us root the tree at an arbitrary vertex. Let us say vertex 1, and this is the tree that has been formed after making this element as the root. But keep in mind that routing the tree at an arbitrary vertex is not really correct in all the problems. For example, especially problems that deal with the degree of the nodes. In that case, you cannot root it at an arbitrary vertex. But in this particular problem, soon we will see that routing the tree at this vertex does not affect the answer because we do not utilize any property of the root. Now that we have rooted the tree at vertex 1, let us think about when will the monster at vertex 1 be killed. Definitely it has to be killed in round 1 or round 2 or round 3 or round n. So there are n different possibilities. We do not know what the optimal round for it to be killed is. So instead of guessing, why don't we do a brute force, or why don't we try all the different possibilities and see which one gives us the best answer. So let us suppose that this monster is killed at round r, and r can range from 1 to n. Now, if this monster is killed at round r, what can you say about the children? These children, they cannot be killed at round r because the problem states that neighbors cannot be killed together at the same time. But apart from that, is there any extra constraints that connects this and this subtree, or is there any extra constraint that makes this and this subtree interact with each other? There is no such constraint apart from the fact that this node should not have been killed in round r. So therefore, if we can fix the round in which node 1 was deleted as round r, then we would like to know what is the minimum cost to delete this entire subtree such that this node should not be deleted in round r. Similarly, we would like to know what is the minimum cost to kill this entire subtree independently such that this node is not deleted in round r. So now you see that each of these subtrees have become independent of each other, and we are asking the same question again in this smaller subtree. So this is just like recursion, wherein you were asking the question on this bigger subtree, but once you added a small constraint to this particular node, you are asking the same question on this smaller subtree. Same for this subtree. So this motivates us towards a DP definition wherein we can define DP of UR is the minimum cost that is incurred when you need to kill all the monsters in the subtree that is rooted at node U such that the monster at node U is killed at round R. So what is the minimum cost to achieve this configuration? Now, if you want to compute the DP value of 1 comma R, you would need the DP values of this node comma everything from 1 to n that is not equal to R. Similarly for this, similarly for this, and similarly for this. So using recursion, you can compute the DP values of this child, this child, this child, and this child. So now you can Assume that once you have called the function recursively for all of the children, you have the correct DP value of all of the children, assuming that each children acts independently, like they do not interact with each other at all. Now your goal is to make sure that you compute the correct DP value of the parent. And again, just a reminder that when you are computing this DP value of node 3, even though this node 1 is connected to node 3, we do not care about node 1 when computing the DP value of node 3, because this is a rooted tree and we should only look down from the node that we are currently at. So now suppose that parent is killed at round PR, that stands for parent round, and the child is killed at round CR. Then what is the penalty that will be incurred by the parent? So if the parent is killed at round PR, then it means that it was alive for the first PR rounds, and the monster in it will inflict a total damage of A of U into PR. This amount of damage it will inflict before it gets killed. Now for this particular node, we can look at all the CR values that is not equal to PR, and then pick out the value that has the minimum damage inflicted, because that is the best that we could do in that subtree. We can do the same for this child, and this child as well, and then we can sum up all the contributions to get the DP of U comma PR for this particular node. For the implementation, we first compute the DP value of all the children recursively. So these are the children. We will first compute the DP value of this children's subtree. Then, as discussed earlier, we will fix the PR value, that is the round at which the parent was killed, and this value can range from 1 to n. Then we iterate over each of the child, and then we try to fix the CR value, that is the round at which the child was killed. But we need to fix it such that it inflicts the minimum amount of damage while also respecting the condition that CR should not be equal to PR. And then we take the one with the minimum amount of damage, and then we add it for each of the children, because it is compulsory to clear out each of the children's subtree. And this way we can solve the problem. Now, what is the time complexity of this code? We have 3 nested for loops. This loop can go till n iterations. This loop can also go till n iterations, and this loop can also go till n iterations, because one node can have n minus 1 children as well. And since this DFS function is called for each of the n different children or n different nodes that exist in the tree, you might think that the time complexity is O of n cube into n, that is O of n to the power 4. But that is not true, and I will show you a trick to compute the time complexity in these kind of tree DP problems. So first of all, notice this observation that the summation of degree of all the nodes is equal to 2 into n minus 1. And why is this true? Because if you look at edge, each edge contributes a degree of 2, one from this side and one from this side. And since there are n minus 1 edges in a tree, so the total amount of degree that can exist is 2 into n minus 1. But we do not need to focus on the specifics. We can just say that the summation of degree is a linear function in n. Now, if you look at the node, so if you look at this DFS function, the time complexity of or the amount of operations that we do for a single node is not exactly n cube. It is something different, because this can go till n, which is fine, this can go till n, which is fine, but this can only go till the degree of the node. So the time complexity is actually, so the time complexity for a single node, or the amount of operations that we do for a single node, is actually equal to n square into the degree of the node. Now we won't just multiply it by n, saying that this operation needs to be done on all the nodes. Instead, we will write this expression n different time and sum it up. So if you sum up this expression n different times for each of the nodes in the tree, you will see that n square, you can take it common from the expression, and then you will get an expression which says degree of this node plus degree of this node plus degree of this node, etc. And the summation of degree is actually a linear function of n. So the time complexity is O of n cube instead of O of n to the power 4. So this is a very powerful trick that you can apply to DP problems. That is, instead of multiplying the number of operations in a single DFS call by n, instead sum up all these values, taking out some of the values common, so that you can get to this expression where you have summation of degree, which can simply turn out to be n. Because yes, it is true that one node can have n minus 1 different children, but then not every node can have n minus 1 different children at the same time, right? So they kind of balance out things between each other. So some nodes do heavy lifting, some nodes do light work, and then overall the amount of work that has been done is only O of n cube. And this is a recurring theme that we will see in all the upcoming optimizations in this video. But how do we optimize the time complexity from O of n cube to O of n square? If you notice this code segment, what is it trying to do? It is trying to take the minimum value of the DP of child such that it is everything from 1 to 1 except one particular value, which is PR. That means if this is the DP value of the children and if this is the PR, it is partitioning the array into 2 points, into 2 segments. So this is the prefix segment and this is the suffix segment. So it is simply excluding this particular green value and then taking the minimum of the array. So if we can compute the prefix sum, so this is nothing but a prefix minimum. So this is a prefix minimum and this is a suffix minimum of the DP array of the children. So if we can pre-compute all the prefix minimum, so this is one prefix minimum, this is the second prefix minimum, this is the third prefix minimum, and so on. Similarly, this is the first suffix minimum, second suffix minimum, third suffix minimum, and so on. So if we can pre-compute all the prefix and suffix minimas, then we can remove this for loop, and then we can simply say that if you want to get the minimum of this segment and this segment, simply look at the prefix minimum till here and then look at the suffix minimum till here and then take the minimum out of these two. For the implementation, we take the same code as before, and once we have computed the DP value of children, before exiting the recursion, we pre-compute the prefix DP as well as the suffix DP that computes the minimum of a prefix as well as minimum of the suffix. So to compute the prefix DP, you start from here and repeatedly keep on taking minima from left to right. Similarly, if you want to do a suffix DP, you start from the back and then repeatedly keep on taking the minima from right to left. And once you have done that before exiting the recursion, by the time you visit the parent node, all the children node will already have their prefix and the suffix minimas already computed. So instead of iterating over all the possible CR values, you can simply say that this is the partition point. Then you need to find out the prefix minima till here and the suffix minima till here. So PR minus 1 and PR plus 1, and take the minimum value out of that to get the minimum value of the entire array excluding this green box. Now what is the time complexity of this? you will see that at each node the number of operations that we do is equal to n into degree, and if you sum them up for each node you will get n into summation of degree, which is O of n square. So this is some progress, but this will still TLE. Now how do we optimize the time complexity to maybe O of n root n or n log n or even O of n? When you are learning DP, the more proficient you become at it, the more afraid you become of taking risks. That is, as soon as you see a problem, you are afraid to think of a greedy approach because you think that a greedy will definitely lead to a wrong answer. However, if you ask a beginner to attempt this particular problem who does not have a lot of experience with DP, they probably will have some unique insight or approach that will most likely be incorrect, but that is actually the key to optimize your DP transitions. So make sure that as and when you become strong at DP, keep an open mind to also think of all the obvious greedy approach that even though are incorrect, they will lead you to something that will help you arrive at the intended solution. So for example, a beginner, if they are attempting this problem, they can say that since a tree is a bipartite graph, that means you can divide it into two sets. One set is colored white and one set is colored black, such that there are no edges between nodes in the same color. And one obvious construction is to color all the nodes at even level in color white and all the nodes in odd level in color black. So you might think that the game can anyway end in two rounds, right? Because in one round you kill all the monsters in odd levels, and in the second round you kill all the monsters in even levels. But that idea is definitely incorrect. Why? Because it is possible that all the monsters that you are delaying for round 2, that will inflict a lot of damage if you keep it till round 2, right? So it might be better to delete them in round 1, but if you do that, then the monsters that you just left out, they can inflict a lot of damage. So there is a trade-off there, and that is why a DP is needed. So even though this approach did not work, it at least gave us some hint that the total number of rounds has to be less, right? It at least gave us some intuition, although that is just a hunch, we need to prove it. The second insight that can lead to the observation that the number of rounds is going to be small and not exactly n is the problem of counting the distinct frequencies in an array. So if you recall, there can be a total of root n distinct frequency. Why? Because if an element with frequency 1 exists, then there is one element. But if an element with frequency 2 exists, there are two elements that have been captured there. Same for element with frequency 3. So if you sum up all the frequency, you will see that it grows quadratically. That means since there are a maximum of only n different elements, you can have a maximum of root n distinct frequencies only. And soon we will see how this observation will help us to figure out that the total number of rounds will be small as compared to n. Now, if a monster is killed at round r, so suppose if this monster is killed at round r, what can we say about the round at which the children are killed? Previously we have discussed that the children should not be killed at round equal to r. But can we say more about it? Can we explore that line of reasoning further? Can we say more? So suppose if this is killed at round 5, can the children be killed at round 1? The answer is definitely yes. One of the children has to be killed at round 1, because if none of these children were killed at round 1, then it means that it was better to kill this monster in round 1 only. Why did you wait for round 5? So one of these children will definitely have round number as 1. Then can a children be killed at round 2? So the answer is definitely yes, because if this is round 5, then the one of the children must definitely be killed at round 2, because if not, this element should have been killed at round 2. Why did you wait for round 5? Then you can continue this reasoning and say that if a monster is killed at round R, then the children, there should be exactly R children or R minus 1 children, and they should be killed at round 1, 2, 3, 4 up to R minus 1. So they should be killed in a permutation of 1 to R minus 1, right? At least the permutation, like there can be more, so it is possible that this is 1 and this is also 1, but at least 1, 2, 3, and at least each element from 1 to R minus 1 should exist in each of the children. So you see, this is just like the frequency counting problem. That is, if a node goes in round R, it says that it has to take R different elements with it. So basically R is the frequency with which this node happens, right? So basically, if this is R and these are the children, so each node adds a frequency of R nodes in the tree. So, and since we know that frequency, the sum of frequency grows quadratically, then it is clear that there will be root n different rounds. So this leads to some hope and intuition that the number of rounds is at most root n, and maybe we can investigate that thought further. But just hope and intuition are not enough, because what if this node is R and it is bringing n R minus 1 different children labeled 1 to R minus 1, what is the guarantee that it is not reusing the old elements? Because this frequency counting problem only works if you are bringing two different elements to the table. You are bringing three new elements to the table. But what if the node at 5 is using this node 4, but this node at 6 is using this node 4 again? Then we are over counting, and then in that case maybe the number of rounds is actually more than root n. So we need proper proof. So even though we do not have a proper proof now, but with this and this approach, we have some idea that we need to explore this direction further on what can the maximum number of rounds be. Is it n, is it root n, or is it something even smaller? Now suppose the game continues for r rounds. We will try to construct a tree with the minimal number of nodes that is needed to let the game continue for r different rounds. Let us start from r is equal to 1. So if you need the game to go till round 1, we need to have exactly one node. What about r is equal to 2? When we need the game to go to r is equal to 2, our goal should be to reuse the old nodes as much as possible. So this is the node that will be killed at round 2. But if it will be killed at round 2, its neighbor should also exist that should be killed at round 1, and we will reuse this node. What about when the game goes till round 3? So if this node will be killed at round 3, we have already established that it must have a children that has been killed at round 1 as well as round 2. So for the round 2, we can try to reuse the old nodes and the subtree, right? Because we need to create the minimum number of nodes. So we take this subtree and we attach it over here. But we also need to attach a node with that was killed at round 1. So our goal is to reuse old nodes. But can we reuse this one that already exists in the tree? We cannot, because there is a path from this to this, because they are already connected, and if you connect it with an edge, you will end up creating a cycle and since a tree can't have a cycle, you will need to allocate a fresh node over here. Then what about when a game goes till round 4? So if a game goes till round 4, you will need to reuse old subtrees. So if this is the node that will be killed at round 4, you can attach this old subtree over here. But if this node is killed at round 4, naturally it must have a node that was killed at round 3 as well as round 2 as well as round 1. So, and of course you cannot use this round 2, you cannot use this node 2 again because it will end up creating a cycle. So you will need to allocate a fresh node over here. But if you do so, may remember that this is also a general node in the tree. That means that if the label here is 2, it should have a children that is equal to 1 as well. That is, you can't just attach a node equal to r randomly. If you are doing that, you need to attach all its valid children as well, which will range from 1 to r minus 1. That means you need to pluck this subtree from here and attach it over here. You can't just attach a single node. Similarly, it should also have a neighbor called 1. So you need to pluck this and you need to attach it over here. Now, if the round goes till round 5, then you can see that you can use the subtree that was created as part of round 4 because we want to minimize the number of nodes. But you also need to attach the subtree of 3, not just 3, the entire subtree of 3 over here. But you also need to attach the entire subtree of 2 over here. And you also need to attach the entire subtree of 1 over here. So you can see that every time an element enters into this tree, it ends up attaching the subtree of all the previously seen elements. So this is in similar vibes to this expression that you might have seen. So 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, summation of all of this is equal to 2 to the power n minus 1. So it is behaving in the same way. And if you want to write it more formally, you can see that every time you attach a node with that ends at round r, you will see that you add 1 because you just added a new node, and then you will need to attach each of the subtrees, not just the nodes, each of the subtree from the previous iteration. So that is why b3, b2, b1 and b4. So that is why the recurrence relation is f of r is equals to 1 plus this, and this formula simply comes out to be 2 to the power n. And the editorial also mentions this formula, but I want you to focus not just on the formula and the proof of correctness, but on the intuition of how 2 to the power n is coming, because every time a node enters, it ends up computing this entire prefix sum and transfer it over here. So this is the prefix sum, you transfer here. This is the prefix sum, you transfer here. This is the prefix sum, you transfer here. So where does this pattern occur? This pattern occurs in powers of 2, wherein the prefix sum of the powers of 2 gets converted to the next higher power of 2, right? And that is why we say that the bit at index n is alone, it's individually more powerful than all the smaller bits combined, and that is actually one of the key insights that we use to solve a lot of bitwise problems. So I hope that it is now clear that if a game goes till round n, there has to be a minimum of 2 to the power n nodes. But since there are already n nodes available in the tree, no more than n nodes, then the game must stop at round log n. And log n is roughly around 20 for the n that we are talking about. So now we have clarified that the total number of rounds that the game will go on for is not n, not infinity, not root n, it is actually just log n. So we don't have to do anything apart from removing the limit of less than equal to n and replacing it with less than or equal to 20 or 22 or something like that. For the code, we will reuse the old code from before where the time complexity was O of n cube, and simply replace n with max round and n with max round. Here max round is a constant which is 22, which is a safe limit for these log n when n is 10 to the power 5. So what is the time complexity? So you can see that this is log and this is degree. So in each node we are doing log square n into degree of operations. So if you sum them up, you will see that the time complexity is n into log square n. Now how do we optimize the time complexity to n into log n? For that, you can notice that we are computing the suffix and prefix minima manually by ourselves. So we can apply the same trick as before and then pre-compute the prefix and suffix maxima not till n but only till log n, because this is the maximum number of rounds that the game will continue for, and then we will utilize that same prefix as well as suffix minima. So this is same as the O of n square solution, except that we are now restricting it to log n rounds, and the time complexity is again log n into degree for each of the node, and there are n nodes. We sum them up, we get the time complexity of O of n into log n. Finally, how do we improve it to O of n? The time complexity is O of n log n as we discussed, but notice that we are iterating PR from 1 to max R, and this is log n. But if you have a node U that is connected to d different children, then it will be killed in round 1 or round 2 or at most round d plus 1. It does not need to wait for round log n. So that is why you can replace this with degree of that vertex, and if you do that, you might think that the time complexity has been optimized to degree sum, but that is not true, because you also need to take the prefix and suffix minima for the entire log n array, because you might need it later. But it is possible to optimize this section as well, to restricting it to the degree of that vertex here as well, but then you need to add some complicated if else here as well, so that you need to take the last element of the suffix dp array and some modification for the prefix dp array in case PR for the parent is larger than the degree of the child. So that part can be done, and you can remove this log n factor from there. But even then the code would not be truly O of n, because this is degree and this is degree. So the time complexity is summation of degree into degree, which I don't think is O of n unless I'm wrong. So yeah, but it can definitely be done. I have seen people post their ideas in the comment section on the Codeforces editorial blog, so you can take a look at it. While designing the initial video, I had planned to add the O of n approach as well, because I was under the impression that adding this line over here would make it to summation of degree, which will achieve O of n. But then I forgot about this inner loop, and then I also forgot about this log n factor over here. But then I realized that it is not worth the effort covering the O of n approach, because anyway O of n and O of n log n are not much far apart in these kind of problems. But if you are interested, you can take a look at the editorial, and the comment section has some interesting ideas on that. And if you have a unique and intuitive approach that you would like to share for the O of n approach, do let me know in the comment section. So all the code that you have seen in this video will be available on cfstep.com. I will add a link to it in the pinned YouTube comments. There you can also find the slides that you saw in this video. And if you have any queries, you can reach out to me on Discord or even on Twitter. Then on my blog, on my website, I have some tutorials on treedp that you can refer to solve some similar problems to apply the concepts that you have learned. And if you want to submit the easy version of this problem, you can take a look at the Codeforces group that I will link in the YouTube comments. And that group also has another contest that has similar problems on treedp.